So Mercury, there are 94 elements in the periodic table, but this is the only one that has its own international treaty. So I'd like to aim this seminar as an explanation of why and an appeal for collaboration. So I'm not going to be talking about today what we've done so much as what we can do together. Now we're one big happy institute. I think we can start to work on where we can collaborate. I've put together some ideas, and hopefully this this presentation will give other people some ideas. So we've got the Minamata Convention with the hashtag Make Mercury History. I'm Warren Cairns. I'm at the ISP of Venice, and so I'm appealing for collaboration in the future with all of you. So the Minamata Convention on Mercury is an international treaty. It's designed to protect human health and the environment from emissions from mercury and mercury compounds. It was approved by over 140 delegates on the 9th of January 2013, and Italy was present as well, and was later signed on the 10th of October in Japan, in the prefecture of Kumamoto, where Minamata, the actual city, is. The Minamata Convention on Mercury entered into force in August 2017, with the first conference of the parties that took place in December 2017. Italy definitively ratified the Minamata Convention on the 29th of September 2020 this year. So we are now signatories of this treaty. And there's even a film coming out in February 2021, if we're allowed to go to the cinema. There's going to be a film with Johnny Depp as a photographer, Life magazine, who documented the fight of the people of Minamata trying to get recognized for the problems that they had in their city. So the Minamata Convention is made up of 35 articles with 5 annexes, and it can be divided into 4 main categories. The first describes the obligations to reduce emissions, releases of mercury and mercury compounds to the environment, and controls on life stages. I think ISP can intervene. We can help with carrying out controls on air emissions and releases to land and water. Storage and waste in contaminated sites is a big problem, because a lot of the mercury that cycles round and round and round is legacy mercury. So mercury is being emitted, it's deposited to the land, re-evaporates again. So we've got a very big contaminated site near Venice called Marghera, which people probably know about. And also we can probably look at health aspects. Even as a polar science institute, there are people that live in the Arctic that eat the apex predators. And it's the apex predators where mercury has got the highest concentrations, because it's the only element that bioaccumulates and in the bodies of the animals. We can help with public awareness and information and education, and obviously research, development and monitoring, which is the main mission of ISP. So there are lots of areas where we can include mercury in our projects and think about how to collaborate all together and with me to affront this problem. So mercury is a problem. I'm sure everybody knows it's a problem because you're all environmental scientists. Mercury can exist in various chemical forms, each of which have got a different toxicity. In the atmosphere, it mostly exists as elemental gas Hg0, and that's a neurotoxin. In the other parts of the environment, in soils, in water, it can exist as Hd2+ or Hg1+ ions, or various methylated forms with increasing toxicity due to methylation. So one of the first industrial diseases that was known was erethism. Erethism mercalis, or Mad Hatter disease, or Mad Hatter disorder, was a neurological disorder which affects the whole nervous system and is caused by mercury. And this is because in the 19th century, mercury in the form of mercury nitrate was used in the production of felt for hats, in a process called carroting, in which the fur became orange because they added orange salts. The fur was separated from the skin using an orange colored solution, that was used. They used mercury nitrate as a smoothing agent. So to remove the fur from the skin of the animals, they used mercury nitrate. And so what did Mad Hatter's disease look like? So Mad Hatter's disease is one of the first industrial problems that we know about, where people identified the source of a contamination that was affecting people's health. So mercury poisoning had a long list of symptoms, including attack of the nervous system, hair loss, nail loss, muscle spasms, slurred speech. Everyone can read all the long list of various unpleasant disorders you can get from breathing in of mercury vapors. And somewhat ironically, Johnny Depp, who's going to be playing the photographer in the film about Minamata, was also playing someone affected by mercury contamination when he was playing the Mad Hatter in Alice in Wonderland. Obviously, the Mad Hatter in Alice in Wonderland is one of the first characters in a book who has been made ill by industrial pollution. So at least for us who study mercury, the Mad Hatter is quite an important character. So mercury ions can produce other toxic effects like protein precipitation, ion inhibition, corrosive actions. Mercury salts are toxic. Methyl mercury salts are even more toxic. Methyl mercury and dimethyl mercury are formed by biotic and abiotic processes in sediments by microbes. A lot of this production is also controlled by the MER gene. So that in recent years, we've actually discovered there's a gene that microbes used for methylating mercury, so we can also start looking for that. And then rather sadly, our knowledge of the toxicity of dimethyl mercury was massively enhanced by Dr. Karen Wetterhan, who managed to contaminate herself with dimethyl mercury, and it took her a year, unfortunately, to pass away, but she meticulously noted all her symptoms, what happened. She was measuring mercury in herself as she was passing away, and handed this legacy to us of a very articulated and detailed account of mercury exposure to dimethyl mercury. And one of the primary laboratories in the world for studying mercury now is still in Dartmouth in the United States, and they're a very large and important research group for studying mercury in the environment. And her passing was a very big shock to a lot of the community. So please don't ask us to measure dimethyl mercury in your samples, because I won't. You can ask someone else to do it if they're mad enough, but I'm not going to do it. So why do we call it the Minamata Convention? Well, Minamata disease was found in the city of Minamata, which unfortunately for the city of Minamata is also quite close to Nagasaki and is just up the road from Hiroshima. So they've not had a good start to the 20th century. It's sometimes called Kiso Minamata disease after the company that contaminated the bay in just outside Minamata. And this city suffered a large number of people who had severe mercury poisoning. They had various symptoms: ataxia, where you lose control of your muscles, numbness in the hands and feet, muscle weakness, loss of vision, congenital defects in the womb. They had fetuses that were damaged, and all of this was eventually found to be due to the fact that this company was emitting methyl mercury into the waters of Minamata Bay. So this was first discovered in Minamata City in Kumamoto Prefecture in 1956. As I said, it was caused by methyl mercury release from the Kiso Corporation chemical factory. And these emissions continued from 1932 all the way through to 1968. This highly toxic chemical bioaccumulated and biomagnified in the shellfish and fish of Minamata Bay, and these were eaten by the local population, resulting in mercury poisoning. We had cats, dogs, pigs, and human deaths continued for over 36 years. And the government and the company did very little to affect to prevent this pollution. The animal effects were severe enough that cats that were eating leftover fish from the fish market started having what was known as dancing cat fever. And so it was this incident that gave us most of our own information on what we know about the toxicity of mercury in people and in mammals. So where do we stand on mercury right now? Well, mercury, unfortunately, although it's got natural emissions, we've got a huge number of re-emission and anthropogenic emissions. So the orange arrows are re-emission of mercury that's already been emitted anthropogenically. And we also have large anthropogenic emissions, and these come from coal-fired power stations. They come from coal-fired power stations and gold mining, getting rid of mercury vapor lamps. There's a huge amount of anthropogenic emissions, but by far the biggest ones at the moment are coal mining and or burning of coal and fossil fuels and artisanal gold mining. And so the mercury goes into the atmosphere, gets redeposited to the land or to the fresh water, and then it gets into the oceans where it then gets re-emitted again. Mercury goes round and round and round and round, and there are research groups specialized in studying the mercury isotopes, because obviously it goes round enough times that you start to get a kind of fractionation. Even though it's a very heavy element, you start to get fractionation of mercury because it's re-emitted and going round and round so often. So they can start to tell whether the mercury that's landing in the Arctic or Antarctica is because it's originally anthropogenic mercury or whether it's re-emitted mercury. There's a huge amount that goes into the oceans. The oceans are the ultimate sink of mercury, and because of this re-emission, they're also the main source of mercury. So we've got mercury coming into the rivers from atmospheric deposition, coming in from the rivers, and we get exchange from the surface in the intermediate deep oceans. We've got natural emissions from hydrothermal vents. We've got deposition of particulate matter that gets picked up by the biota and either sinks to the bottom or then gets re-emitted again. And so we've got huge transfers of mercury going through the ocean. So that's another place where we can also hope to collaborate. Obviously, mercury then gets to the Arctic. All these processes occur after very long range transport of mercury to the poles. It occurs in the Arctic and the Antarctic. We get atmospheric deposition. Mercury, because it's a gas, can have very long range transport because it's atmospheric residence time is about a year, so it can get all around the hemisphere. At the moment, we still don't see a lot of exchanges between hemispheres, but the mercury that's emitted in the northern or the southern hemisphere can go all around that hemisphere. And we get exchanges between sea ice, the ocean. We get resuspension between sediments. We get nutrient regeneration. We get deposition and resuspension from the shelves. We got methylation and demethylation going on. And so there's all sorts of processes. There's atmospheric processes, photochemical processes, all happening in the Arctic. So it's a very active part of the chemistry of the Arctic. And with climate change, these numbers are starting to change. Obviously, as the permafrost and the glaciers start to melt, we're getting increased anthropogenic emissions. We're getting increased emission from the permafrost and glaciers because the permafrost and glaciers are legacy sinks of mercury. And so as they melt, we're getting emission of mercury that was emitted in the 1950s or earlier, that as it's now being remobilized again, re-emitted into the Arctic Ocean. We're getting increases as the sea ice becomes less permanent. We get bromine explosions and other things happening in the spring. We get large re-emission of mercury because we don't have ice acting as a barrier anymore, stopping the emission of mercury. And so you can actually look at the mercury cycle and the chemistry of what's happening and it can get complicated very quickly depending on how in depth you want to look at it. So there's an awful lot of processes we can all start to look at together. We've got biological process, we've got geological processes, we've got chemical processes, we've got processes with the glaciers, with the permafrost, with the biota. It's being uptaken in the food web. It gets into the food web and is uptaken by the local people, or even by us if we import food from the Arctic. And so you can see as we change and go up the food web, you can see the amount of methylmercury goes up as the higher you go up. So in the atmosphere, we've got mostly mercury 0. In the snow, the permafrost, it's mostly mercury 1 or 2 plus, ionic mercury. And then as we start getting higher and higher up the food chain, you see the amount of methylmercury starts to go up. And this is why methylmercury and mercury is so important, is because methylmercury is by far the most toxic form that commonly happens in the environment. And so we can see here again the concentrations going up in parts per million. And so by the time you get to Arctic cod and beluga, which are what the local people, the local population are eating, you're starting to get very large contamination with methylmercury. There are still lots of gaps in the knowledge. We don't understand the atmospheric mercury depletion events to happen very well, because what happens in the Arctic is you get very, very active oxidizing conditions in the spring. We've got, when the sun comes out, we've got bromine explosions, we've got reactions with ozone happening, and those reactions cause oxidation of mercury from the gaseous form into an ionic form, and that then deposits on the snowpack. What happens to this mercury once the snow melts and enters the marine systems, we still don't know. Methylmercury can enter the Arctic food webs, and there's still a great need, in fact, understanding how the Arctic marine system cycles mercury, and it's all linked with the availability from organic carbon and the availability of inorganic mercury in the water. We can look at, there's still a lot of need to look at the wildlife. What are the effects of multiple stresses? Obviously there's mercury in the environment, but there's other other persistent pollutants as well. So what are the effects of those, and on their nutritional factors? What effects do they have on the toxicity of mercury in the biota? We need to start addressing some of the gaps we still have in mercury models. And then we need to see what the effect is on human populations and what choices they can make to mitigate these problems. So we're doing some of these things already in Venice. As I said, this isn't to show an overview of our work or whatever, but we're starting to look at the atmospheric mercury depletion events. We've been working with our colleagues in France and through various projects for a long time now. In the Arctic spring, we get emission of bromine from the sea surface. As Andrea showed in one of his presentations, this bromine reacts with ozone and the light and causes the formation of ionic mercury, which then falls down with the snow. It then gets deposited in the snow. It can then, with sunlight, be re-emitted to mercury 0 and then be redeposited again, or it can get into the water. And so we've got, we're studying how this long-range transport of mercury happens, what the deposition events are like, how quickly they happen. We've seen that this deposition and re-emission can happen over a period of hours. So we're gradually increasing our sampling time. We're working with our colleagues to measure the mercury in the air at the same time. And this is one of the reasons why I collaborate so closely with Andrea, because he studies bromine as a marker for sea ice, and bromine is very active in the mercury cycle, because it's what reacts with mercury to cause a crash out and precipitation. We still don't understand all the photochemistry, as a recent paper has shown. We've still got some oxidative processes that are missing. Some of the papers we've published, we've been looking at diurnal circles of iodine, bromine and mercury in Svalbard. We've done similar experiments in Antarctica, looking at how mercury is deposited and re-released from the snowpack at Dome C. We've worked with our French colleagues in Svalbard in the past, looking at mercury during mercury depletion events, because these events cause, as I said earlier, large depositions of mercury onto the snowpack. In ICOOP, we're working closely with our French colleagues again to look at how mercury is coming out of the soil and the permafrost and how it's getting into the Arctic Ocean. You can see the various concentrations they're starting to find. We're getting a huge amount of mercury going into the Arctic Ocean as the permafrost melts, and then that mercury is then re-emitted and gets exported back down to us again. And so our colleagues are looking at the modeling of halogen and ozone chemistry and its influence on Arctic chemistry, because they've noticed that without halogens, you don't get a good model. This red line is the modeling of ozone at 2 Arctic points. And the model works very well between May and August. So you've got the observed ozone in black, the modeled ozone in red. But in the spring, when you get these bromine explosions, there's a very big digression between the model and the observed results, and that is because we don't fully understand the halogen chemistry yet. So without a good description of the halogen chemistry, we can't describe well the ozone or the mercury chemistry that's happening. And so we're working with our French colleagues to give data to try and improve that. So there are many places where we can collaborate. We can look at mercury in the biota. We can do biotic and abiotic mercury methylation processes. We can start to look at amplification in the trophic web, mercury in oceanic surface waters and its availability after the permafrost melt. And with that, I can finish my presentation and